In this video, we present our CVPR 2025 paper, HybridMQA, Exploring Geometry Texture Interactions for Colored Mesh Quality Assessment. We start by discussing our task. Colored meshes are dominant 3D formats in many real-world applications, including VR, AR, and gaming. As visualized here, colored meshes are defined by their shape, or geometry, and their color, or texture. Given these components, a rendering algorithm is used to render projections of 3D colored meshes. Our task is to assess the visual quality of a mesh under real-world distortions, such as compression and transmission. To achieve this, we made an important observation. We find that geometry and texture of meshes interact in complex ways that affect their visual quality. In other words, either the geometry or texture can affect the appearance of distortions in the other. This effect is visualized here. In the first row, starting from a pristine model, we first perturb the geometry and then change the uniform texture to a complex texture. As a result, the geometry distortion becomes imperceptible. We do the opposite in the second row. Starting from a pristine mesh, we first perturb the texture and then change the uniform geometry to a bumpy one. As visualized in local windows, the noisy texture becomes smooth as a result. This highlights the need for mesh quality assessment methods that capture these complex geometry-texture interactions. However, existing works ignore these interactions between geometry and texture. Instead, they assess quality based either on geometry, using model-based methods, or on texture, using projection-based approaches. To address this, we propose a hybrid method, which consolidates the strengths of both model-based and projection-based approaches and explores geometry-texture interactions to achieve comprehensive quality understanding. Let's now take a look at our proposed HybridMQA framework. It's made up of three main components: the model branch, shown in red, the texture branch, in green, and the quality encoder, in yellow. Next, we'll take a closer look at each component in more detail, one at a time. In the model branch, 2D normal, vertex, and texture maps are first processed by a base encoder, which is a shallow CNN, to extract initial quality-aware representations. These representations capture the mesh's 3D shape and surface characteristics. Next, we build what we call the feature graph by sampling vertex features from the output maps of the base encoder. This graph is then processed by a GCN, which learns richer 3D surface representations. Finally, our novel feature renderer generates 6 perpendicular 2D projections of these learned features. We call these projections 3D feature projections. Our feature renderer is fully differentiable and enables end-to-end optimization of the GCN and the base encoder. Alongside the model branch that learns 3D surface representations, we also have the texture branch, which has a much simpler structure. It consists of just an RGB renderer, which renders 6 perpendicular colored projections of the input mesh. Now, to bring the outputs of both branches into alignment, we ensure that the two renderers use the same camera poses. This allows for pixel-to-pixel alignment between the 3D feature projections and the colored projections, which in turn lets us effectively explore geometry-texture interactions. Finally, we arrive at the quality encoder, the last major component of our framework. This is where we capture geometry-texture interactions and obtain a final representation of mesh quality. We'll take a closer look at the structure of the quality encoder next. Inside the quality encoder, given the two sets of aligned projections, we start by patchifying them and removing background patches. The remaining patches are then encoded into multi-scale representations. We then pass these representations through cross-attention layers, where we capture their interactions and mutual influence. Finally, the resulting multi-scale representations are concatenated into a final mesh quality representation. HybridMQA is a full reference method. Given a reference and a distorted mesh, we process them separately to get their quality representations. The difference between them is then mapped to a final quality score. To show the effectiveness of HybridMQA, we compare it against 11 model-based and projection-based full reference methods across 4 public datasets. We measure performance with 2 correlation-based metrics, SRCC and PLCC, where a higher value indicates better alignment with human perceptions of quality. As we can see, HybridMQA consistently outperforms all existing works on every dataset. Here we apply GradCam on 3D feature projections to verify that the model branch effectively captures geometry-aware quality representations. As we can see, HybridMQA understands 3D geometry and attends to regions with geometric distortions, aligned with human perception. Here we apply GradCam before and after cross-attention to show the effectiveness of HybridMQA in exploiting interactions between representations learned in texture and model branches. As we can see, cross-attention successfully identifies and attends to perceptually important regions by exploring geometry-texture interactions. That's it. You can find more results, poster, code, and pre-trained checkpoints on our project page. Thank you for listening